So today, for our second speaker, we have a local speaker. So we have Yanqin Fan. So Yanqin, she is a professor of economics here at the University of Washington. Prior to joining the UW, she was a Centennial Professor of Economics at Vanderbilt University. And she's a fellow of the Journal of Econometrics and the International Association for Applied Econometrics. And Yanqin has broad interests that concerns as statisticians, like she works on several things that are related to what we do. For example, partial identification shows up a lot in causal inference, which I guess is going to be the topic of today's class. So she works in non-parametric econometrics, partial identification, policy learning, and applications of optimal transport in econometrics. In fact, we just had, there's an optimal transport workshop recently, right? Her work has been published in various academic journals, and she'll start her term as a co-editor at the Journal of Econometrics in January 2025. So without further ado, Yanqin, please get started. So just some rules. So we're going to save the questions until the end. So we're going to have about 50 minutes, and then we're going to have 10 minutes of questions in the end. Okay?
All right.
Thank you.
For the nice introduction and for the for the invite, and thanks everyone for coming. So I'm going to talk about some work in progress. So your feedback and comments will be very useful for us in the last stage of wrapping up the paper. This is joint work with Brandon Potts and his mathematician and expert on optimal transfer. And Xuetao Shi, he's a former student of mine, and he's an AP now at University of Sydney. And the title, is a bit long. So I'm going to start with, the moment model, and then talk about incomplete data, and then talk about partial identification. And then, once I talk about partial identification, hopefully you'll see, the role of optimal transfer played, in this work. You worked before?
Wait, let's see here. I guess. Oh, maybe you just need to click here.
Okay, so the model, in fact, we study in this paper is a well-known class of moment models in econometrics. And the parameter of interest, theta star here, is characterized by a finite number of moment conditions. And so M is the moment function of dimension denoted by K. And the random vector in this model is denoted as W. And W follows the true distribution denoted as mu of O. You can think of this as distribution function on probability measure. It doesn't really matter. So the expectation with subsequent O here is taken with respect to the true distribution of W. Now, in this talk, I'll mainly focus on the identification of theta star. So the identification, of theta star, of course, depends on the type of sample information available. So to be clear, let me decompose, the random vector W, in the model into three parts. So Y1, Y0, and X. And all three, are random vectors. So Y1 is of dimension D1, Y0 is of dimension D0, and X is of dimension Dx. So in standard, econometrics classes textbook, what we assume is that we have complete data. So what do I mean by having complete data? So what this is, well, remember there are three components of W, but all three components are observed in the same data set. So that we have one data set and y1, y0, x are observed in the same data set. So in this case, then of course you know that the expectation of the moment function is identified for any theta. So it can be estimated by the sample mean. So the identification of the two parameter theta star now just it's kind of standard, relies on some run condition. So as long as some run condition holds, then theta star is is identified, and we can use GMM. So in metrics, we call that's generalized method of moments. I believe in statistics is GEE, generalized estimating equations. But in any case, as long as we have complete data under simplifications, theta star is identified and can be consistently estimated, and inference can be done. This is now on well developed. Just to refresh your memory, let's look at this very simple example, linear projection model. So in this case, theta star is what we're interested in, and there's this orthogonality condition. So this orthogonality condition implies that theta star is characterized by a moment condition model like this, where the moment function is just given by this error multiplied by the covariance. Okay. Now with this, then you see when complete data is available, then we can estimate the mean of each term. This term, the mean of that term, and the run condition in this case, means that the expectation of this matrix is non-singular. And given this run condition, then we can, identify theta star, which is you just take the inverse of expectation multiplied by the expectation of this term. And then, of course, we know, the commonly used estimator in this case is ordinary squares. And we know, ordinary squares is consistent, asymptotic, normally distributed, and so on and so forth. So I can do that. Okay? But in some applications, in fact, important applications, not all the random vectors y1, y0, x are observed in the same data set. And one simple example is y1 and x are observed in one data set. We can call this, say, the main data set, but y0 is not observed in the main data set. But oftentimes, another data set is available. We can call this, let's say, auxiliary data set. And the auxiliary data set on just say the second data set contains observations on, both y0 and x. But we don't have, any data set that contains observations on y1, y0, and 3, and x on 3 random vectors together. So in this case, this is an example of incomplete data, and in econometrics, this belongs to data combination. I think in biostatistics, it's often called data fusion. Now, here are just a list of examples for which indeed the data sets come in this way, two separate data sets. And what's important is that in these examples, and the two data sets cannot be matched. If you have an identifier that you can use to match the data sets, then that's not a problem. But oftentimes, the two data sets cannot be matched. So let's just go through these examples. And one here is in economics, we are interested in long-run returns to college attendance. Okay, so this is a very important issue in labor economics. But some variables, long-run returns, and some variables characteristics that affect college attendance can be observed available, in PSID on NLSY. These are commonly used longitudinal data, in economics work, but it has been sort of suggested that college attendance depends on other factors as well, like genetic factors on whether your friend goes to college. but these variables are not observed in these two data sets, but typically they are available in ad hoc data. Okay? So in this case, if we want to account for all the potential variables that affect college attendance, then we need to combine these two data sets, PSID with ad hoc and LSY with ad hoc. And also for these two data sets, there's no identifier. You can't really match individuals in one data set with individuals in the other data set. And another example, algorithmic fairness, I'm going to use this as a one running example for my talk today. This is now a recent popular example for which data combination is really important because of privacy issues, right? In algorithmic fairness, there's decision outcome, and typically there's protected attribute. But the protected attribute is not observed in the same data set as as a decision outcome. So the question is, if I'm interested in estimating measures of algorithmic fairness, then we have to combine both data sets. And the third example, this in fact is a very interesting example in causal inference, and researchers, and also, people like Amazon, in fact, are very much interested, in this topic, because business, Amazon, they interested in long-term effects of, some intervention, and then they run, random experiments, but they can't run the experiments for very long, so that in their experiments, in fact, they don't observe, the long-term outcomes, but there are often some observational data in which, long-term outcomes are indeed available. So the question is, how do we combine, for instance, an experiment with observational data in order to estimate long-term treatment effects? And there's this recent paper by Asia et al. In fact, studies this issue. And lastly, this is obvious example, right? In DID, if we have panel data, then that's not a problem. We can use DID to estimate treatment effects, but oftentimes we don't have panel. So what we have is repeated cross-section. And for repeated cross-section, we can't really match the individuals in different time periods. So this is another case of data combination. Now, all right, so hopefully I convince you with these examples that indeed data combination, multiple data sources, this is in fact very popular. So we need to make use of multiple sources to identify, estimate, and make inference on our parameter of interest. So technically, then what's the challenge, right? Compared with complete data, what does incomplete data bring to any competition on statistician? Well, if we look at remember the moment model, this is the left-hand side of the moment model, the expectation of the moment function, right? Now, with complete data, we can identify this expectation. But with incomplete data, for a general moment function, we are not able to identify this moment function because the moment function depends on the joint distribution of y1, y0, x. Then given two separate data sets, unless we know more about the data, the dependent structure between y1 and y0, or the structure of the M function in general, we are not able to identify this expectation. Then the question is what can we do? And that's the second part, partial identification comes in. So although we are not able to point identify this expectation, in turn, the parameter of interest theta star, but the sample information we have, in fact, has information, imposes some restriction on the joint distribution, the true distribution of W. And that information, the restrictions will allow us to, partially identify the parameter theta star, although, the information is not enough to pin down one specific value of, the parameter. So that's what this paper is about. So let me just be more precise about the data structure and our assumption. So we have two data sets, and the first data set identifies mu1x, the joint measure on the distribution between y1 and x. And the second data set identifies mu0x, the joint measure on the distribution between y0 and x. Okay? Now, of course, then we have to link these two identified measures to the true measure mu0, and that's our assumption here. This is like comparability assumption. So we assume that the true measure mu0, remember this is a joint measure between y1 x y0 on y1 y0 x. So our assumption here is that the projections of mu0 on y1 x is exactly mu1 x. So that's identified by the sample information. And likewise, the projection of mu0 on y0 x is identified, from the second data set and denoted as mu0 x. Okay, so now, those of you who sort of know OT sort of see, at least start to see the relation between this, and OT. So essentially, for what we're interested in depends on a joint measure, mu0, but what we can identify from the sample information are two bivariate marginals, mu1x and mu0x. So we want to make use of, the identified bivariate marginals to say something about the parameter of interest theta star, which is potentially dependent on, the joint measure. Okay. All right. So let me just quickly mention, the generality of the results in this paper. First of all, we can M is general, apart from we make some continuity assumption on M, but M can be general. In particular, we are not assuming that M is additively separable, and this has been done in existing work in the literature. And also, y1 and y0, these two are important because they are not observed in the same data set. And we allow them to have any finite dimension, d1, d0, or any finite dimension. And also, the number of moment conditions, k, can be any finite integer. And the parameter of interest, could be theta star itself or a known function of theta star. I'll show you where examples, one this case, and the second case is theta. The parameter of interest, in fact, is a known function of theta star. Okay. Now, what has been done? Some special cases have been studied in the literature. So what has been done? Well, the first case is, if you know your moment function is additively separable in y1, y0, then you see under standard conditions, this is identified, even from two separate data sets. And then again, you can just mimic what's done for incomplete data, assume run condition and so on and so forth. Then you can point identify the parameter of interest, theta star, and subsequently make inference. So that has been done in the literature, and in fact, this paper belongs to this category. And the second case is, M is not additively separable. So then, genuinely, M depends on the joint distribution between y1 and y0. So in this case, we cannot, in general, we cannot point identify theta star. Then what can we do? Well, in all the existing work, assume that y1 and y0 are univariate. Okay? So what does this buy us? If y1 and y0 are univariate, then remember we can use coupler to couple the distribution between the marginal distributions and get a joint distribution. So that's one technique that is used in my paper with my colleague Jing Tao and my co-author Xuetao Shi in the journal of econometrics. So we use coupler to couple the two marginals, and then let the coupler vary in a pre-specified class, and then study the identified set of the parameter theta star. And the second case is when y1 and y0 are univariate, then for some functions m, for instance, if m is supermodular, then we know by monotone rearrangement inequality, then we can upper bound and lower bound the expectation of the moment function. So then this means that theta star satisfies two moment inequalities. Okay? And that in turn gives us an identified set of theta star. But you see here, in this case, k must be 1. So we have only one moment function, then we can bound the expectation and subsequently study the identification on identified set of theta star. So to sum up, existing work in the literature make assumptions either on M, the specific structure, or on the dimension of y1, y0. So there are, of course, situations for which these assumptions are violated. Then our purpose is to provide a general, in fact, methodology for studying the identification of theta star in this general model. And of course, the identified set, and the results must be implementable. Okay, so I'll make clear, later what I mean by the results being implementable. So unusable. So I should say easily usable. Okay, I'm going to use two examples to illustrate our general result. So this one I mentioned before, linear projection model, right? So now our assumption is that we identify the two bivariate marginals, but we don't identify the joint. Okay, so let's look at this very simple example and then see what what happens. So this is a moment function. Okay, so if you look at it, this term is fine because it only depends on y0 and x, so that's identified. Right? But then we take expectation. There's expectation of y1 and y0. Right? Expectation of y1 and x, that doesn't matter because that's unidentified. Right? So when we look at we need to handle expectation of y1, y0. Right? Now this model, in fact, has been studied in these two papers, but they only provide the identified set of theta star when d0 equals 1, and that's when y0 is univariate, a scalar. Okay? Now remember I mentioned before, there's monotone rearrangement inequality, but that only applies when y1 times y0 is is of dimension 1, is a scalar, right? But then let's look at what happens when y0 is of dimension 2, let's say. Then y0 has two components, let's say y01 and y02, right? Now when we look at this expectation, then this becomes a vector, right? So existing work apply monotone inequality to each of these two terms. Okay? Now then you see some information is not used when you apply monotone equality to these two terms separately. What information? Well, the dependence between these two, right? Because Y0 is observed. So we observe, identify not only the marginals of Y0, but also the dependence. So this is why, existing work, in fact, provide outer set when the dimension of B0 is larger than 1. And with respect to this example, our distribution is that we provide, in fact, the identified set for any D0. So effectively, we make use of all the information, on Y0. Okay? This is a sort of a simple standard econometrics example. Now let's look at, this more interesting one. It's in fact a simple setup. Y1 is some decision outcome. You can say it's positive outcome if Y1 takes 1, negative outcome if Y1 is 0. It doesn't matter. You can say loan application, job application, anything. So this decision could be made, by humans or by machine. Okay, it doesn't really matter. So we have Y1 and Y0. This denotes cap J crushed on categories. And this is a sensitive variable. So, it's a protected, attribute. Okay? Then X denotes just some other observable covariance on proxies. It doesn't really matter. Now, in this setup, so because of, fairness issues, the decision outcome and, the sensitive class attribute are not observed in the same sample. So there's the main sample that contains, the decision outcome and other characteristics, but then there's an auxiliary sample which contains, the observations on the sensitive variable and also other characteristics. Okay? So one parameter that is of interest, in this setup is measures of algorithmic fairness and different measures that are proposed. And in this presentation, this talk, I'm going to just focus on one measure. This is the simplest one to analyze in this setup, but some other ones are also, very interesting. We studied in the paper. So this is called demographic disparity measure. So I'm just say DD measure. Okay? Now this DD measure, this is notation between any two classes on two categories, AJ and AJ dagger. And the definition is also very simple. It's just a difference between two conditional probabilities. Okay? So look at the conditional probability. Then, the DD measure between these two classes is just the difference between conditional probabilities of, say, a positive outcome for two different classes. So that's, that's very simple. Now, in this, of course, if you just look at it, right, it depends on both Y1 and Y0. So with two separate data sets, this is not point identified. And in fact, Callis et al., studied, this issue from the perspective of data combination. And that's, this is one example that motivated our work. So hopefully I'll be able to show you, the different approaches that Callis take and also we take, and you see the advantages of our approach. So I'm going to spend some time summarizing Callis' result, and then I'll move on to the main results in our paper. Okay, so let's look at there are J categories. So let's look at J-1 such measures together. So this is what Callis et al. Did. So the last class is fixed, and then we look at the DD measures between each of the first J-1 classes and the last J class, the last class. Okay. Now remember I showed you this is the definition. So you can just simply write it in terms of joint probability and then marginal probability, and then apply the law of iterative expectations. It's all very basic, very simple. Then you can write, the DD measure, any DD measure in this form. So the difference between two conditional probabilities now written in terms of expectation. Okay? So what you notice here is that let's just look at the first term, right? In this first term, then you recognize this conditional probability. It depends on three variables: y0, y1, and x. So given the two separate data sets, this probability is not point identified. Okay? Then just by the definition of the identified set, what do? Well, you just run like this term be anything that is consistent with what you observe, then that's an identified set. Then that's exactly what Callis all wrote, for the general case J. And so we summarize it here. So this is identified set. You replace with the true conditional probability by any probability do the same thing here. But this conditional probability, remember, satisfies some conditions, right? So it's conditional is probability, so this must be probability, and also it's conditional probability, so it adds up to 1, so that must adds up to 1. Okay, and also remember we have sample information, right? With sample information, then we can use law of total probability. So the conditional probability must satisfy property 3, right? So you look at property 3. This is identified from the second data set, and this is identified from the first data set. Okay? So these two marginal conditional probabilities impose restriction on this conditional probability. So nothing else. And the identified set, then it just any difference between two terms, expressions like this, such that the PJ here satisfy these three properties, and that's identified set. But then, of course, you can argue, you can sort of ask, right? So that here comes what I said earlier. Whether this is easily computable or easily usable, easily implementable. Well, it's identified set, correct? But how do we use it? What are the properties of this identified set? So it's not very clear, from this representation of the identified set, what the properties are and what can we say, about it, except in the special case where there are only two categories on two protected, classes. So in this case, things become much easier because in this case, remember there's one DD measure, only two classes. So one DD measure, so we can write it. This is the expression earlier. Now, and this probability, because there's only two classes, so it's this, and then you see the DD measure is increasing in this conditional probability. Okay? Then now we can write this conditional probability as a ratio between the joint and the marginal, right? And then now we can use the Fashio-Hopding inequality. It's just a special case of monotone rearrangement inequality to bound, this conditional probability. Okay? And the lower bound, upper bound, when or replacing, this probability, and that one gives the lower and upper bound of, the DD measure, and also the identified set, in fact, is a closed interval. So in this case, it's very nice. It's closed interval, and the lower bound, upper bound, both have closed form expressions. This is very nice. But when it gets to, the general case, more than two protected classes, things become sort of ugly. So what Callis et al. Suggest to do is to characterize, because this set is a convex set. So they suggest to use the support function of this, this set. Okay. Then we know, there's unit sphere, and that's the definition of the support function. So they wrote down, the support function. But if you look at this, this is essentially just the definition of the support function, right? And these three properties still need to hold, right? But if you look at it, well, it is a linear programming problem, but in fact, it's not an easy one. It's an infinite dimensional linear programming problem, right? So they suggest to numerically compute, the support function at different directions, and then they, suggest another algorithm to use the support function to compute, the unidentified set. Okay, now you see what we're able to do, in fact, is to solve this, the infinite dimensional linear programming problem. You see, we'll give closed form expression for the support function, and for any number of protected classes, and in fact any number of DD measures that includes catalyst of course. All right, so here's let me just finish this one. So in fact, what we're able to do is we can look at any collection of DD measures between any two classes, okay? And for any subset of such collection of DD measures, we provide a closed form expression for its support function, and of course this includes catalyst. Okay? So what did we do? Well, of course we cannot use the same approach that catalyst did, at all used. So we instead re-express this problem as a moment problem, so moment model. That's what I introduced earlier. And this example, in fact, it's amazing. If you look at it, it's a very simple example of a moment condition model. Why? Because, well, remember that's a theta star, right? So this is just a conditional probability, right? We can write it as joint probability, and then divide it by the marginal. And the probabilities are expectations. So this is a moment function for theta 1, and we can do this for all thetas. So we put all these thetas together, and that's our vector theta. And the two thetas, theta star, must satisfy this moment condition. Okay, so this is our model. Then we apply for this example. So we apply our general result to this moment function, and that gives us the identified set of theta star. And you may say that, okay, so in this example, theta star is not the parameter of interest, but that's fine. What's the parameter of interest is a simple linear transformation of theta star. So any nice properties of the identified set of theta star will be in fact translated into similar properties of the identified set of the DD measure. Okay. All right. So how much more time do I have?
15 minutes.
Okay, 15. Yeah. Yeah. Okay. So in the rest of my talk, I'm going to present the general result for the identified set of theta star for a general M. And then I'll look at a special class which includes both examples. And then I'll probably skip the linear projection model. I'll jump immediately to the DD measures. Okay. So for the general case, remember this is what we'll work with, assumption 1. And this is also familiar to those of you who know OT. So this is just the Fachet class of joint measures whose projections are mu1x or mu0x. Okay? So in terms of this notation, then we can of course easily write down the identified set of theta star. What is it? Well, theta star satisfies this moment condition. So any theta in the identified set must also satisfy this moment condition for some measure mu, which belongs to this class. Okay, so this is the identified set. In fact, in terms of our formulation, this is what Carlos wrote down, but not in terms of the moment condition. And our second condition is also I think it's a basic assumption. So we assume M is continuous in Y1, Y0, and X. Okay? So with these two assumptions, we can show that, in fact, this identified set is the same as this new set we defined, theta O. Okay? So if you look at this new set, theta O, the left-hand side, this is identifiable for any given theta. This is identifiable from the sample information, right? Now, this in fact is a variation of optimal transport cost, right? If you want to literally relate this to optimal transport, then you can use this result equivalence to this is the same as this, and this is a conditioning method in a very early paper by Ruchendorf, right? Then you look at this inside. This is exactly an optimal transport cost with ground cost given by this one. Okay, so at the most general level, then we have characterized the identified set of the theta star in terms of a continuum of a continuum of inequalities involving optimal transport cost. Okay? But this, of course, is very general. Now let's look at a special case where the M function has this special structure. It's linear in theta, and but it's not additively separable in Y1, Y0, because that's not what we're interested in. And there's this part. Okay? Now you can just replace in the previous optimal transport problem, replace M with the sum of these two. Then you can easily see that this identified set on the new side is characterized by a continuum of much simpler inequalities. Right? Look at this one. Theta appears here. And this is, again, optimal transport cost. Okay? But this set is of a very nice structure, right? Because, it's linear in theta here. So we know immediately it's convex. Okay? It's convex, then, I'll refresh your memory later. But both examples I showed you, in fact, have this structure of the M function. Then because the identified set, this one is convex, so it's characterized by its support function. Okay. Now, if this expectation is non-singular, then you easily see, right? We can compare this one and this there. Then we can easily find the support function of theta star, and it's given by, again, you look at this is a variation of optimal transport cost. Okay? Now then, let's apply this result to the QQ measure. Given in the interest of time, I'm going to skip the linear projection model. If there's time, I'll show you some beautiful pictures at the end. But let's move on. I think this is more interesting. So let's look at this example, right? So this example, remember this is the moment function, right? So this is M1, very simple. And this is M2, again, very simple. Okay? So we apply, the previous result to this example, then we can characterize the identified set. for theta star. Remember, this is any collection of DD measures between any two classes. Then you see this identified set, in fact, is very simple, right? It's also a very nice structure, linear in theta, and there's no optimization involved at all. And this is because, the optimal transport problem earlier for this example has, the closed form. Okay? And also we can find, the support function is also closed form. Okay? Now remember I showed you, what Callis did, right? We are doing the same thing. So the parameters, are exactly the same. So that's why I said that, in fact, here, we effectively solved the infinite dimensional linear programming problem that, Callis introduced to characterize, the support function. Okay, so let me finish this slide. And as I mentioned, this is for theta star, right? It's not for DD measure. But the DD measure, as I mentioned, it's just a linear transformation, right? So any number of DD measures can be written as, a matrix times theta star. And so from the identified set of theta star, we get immediately the identified set for, any collection of DD measures. And also this one is nice because, the measure is a linear transformation of theta. So we can also, derive the support function for the DD measure, and this is all very easy. So there's no numerical optimization, is needed at all. And in fact, an interesting exercise we did is, we use our result, here the support function to compute the lower and upper bound for one DD measure. Okay? You look at it, the expression in fact looks very different, but they essentially they in fact reduce to what Callis derived. But what Callis derived, remember, was for two classes only. And our result here shows that if you're just interested in one DD measure, for instance, this one, then it doesn't matter what the big J is, how many classes you have, the closed interval, the identified set is the same as in the case of two classes. Okay. All right, so let me, do I still have?
Yeah.
Huh?
Yeah, 2 minutes.
2 minutes, okay. So because I skipped this example, so I'll just show you some graphs. Okay, so let me explain these graphs. Now, remember I mentioned that, so this is for dimension 2, okay? And this rho parameter measures the dependence on correlation between these two, okay? Now, existing work, for instance, percentage work, ignores the dependence because they apply monotone rearrangement inequality to each component separately. Okay, but we make use of the entire distribution of y y0. So then you see the green one is the identified set, and the orange one is the outer set derived in existing work. And as rho changes, you see the identified set change, but the identified set, of course, is always contained, in the outer set. So let me just conclude. Well, I guess I'll just mention that we this moment equality model, in fact, is very general. Many examples may not look like, if you look at it just literally, may not look like a moment equality model, but in fact, you can in a lot of cases, you can define, the parameter theta star in such a way that, theta star, in fact, satisfies some moment equality model. But the parameter of interest may be some transformation, maybe even nonlinear transformation of theta star. And one example of, the algorithmic measures we look at in the paper, indeed is a nonlinear transformation of theta star, but still theta star satisfies the nice special case of the moment equality model. We haven't really done much about estimation. It's kind of straightforward, but we haven't really done much about inference. But we believe for the DD measure in Kelly's, they work out inference for the case of J equals 2. That's because the measure, the identified set is a closed interval or it has closed form expression, so it's easy to do. But we have derived the closed form expression for the support function for the general case. So we believe, estimation and inference could be, well, not easily, but could be worked out. And that's something currently working on. And some references. Let me stop here. Thank you for listening.
Okay, so we have 5 minutes for questions. Okay, Fang.
Hi, Yanqin. I have 2 questions. The first question, can I go to assumption 2?
Okay. Assumption 2 is a continuity.
Yes. Yes. So you assume M to be continuous. Mason's function is independent function.
But that's a discrete. Discrete is always continuous.
So the continuous is with regard to what? The metric. The metric is so are you suggesting?
Yeah, I mean these are y1, y0, x. These are only Euclidean space. The continuity.
Because usually the continuity assumption is between 2 topologies. Right. So here you are specifically targeting at a discrete sense, open sense. So the continuity assumption is not what we think about continuity.
Right.
It's more like, okay, got it.
Yeah.
And I have
ask Brandon Pouch about it.
no, I got it.
That's all I said.
Sorry, your measure is y1, y0. Okay.
Yeah.
What is my special? I forgot. So I will let others ask, and I will think about this message.
Yeah, in fact, when Brandon proved, this theorem.
Oh, I remember.
Yeah, because in fact, for a long time, I sort of knew, this way, but I didn't know how to prove it.
Yes.
And so Brandon, they sort of figured out this minimax theorem in some journal, journal of convex analysis. Journal of convex analysis.
Okay, so that's actually related to my second question, because this result is surprising, and I would love to ask, for example, in the common moment equation models, even without any missing data, also we can have a set of rules, right? So that set of rules may not be convex. So even without any missing data. So that means here we have some assumptions about like for example, M can only give us one identified sign. So do we have assumption about like the original no missing value version is identifiable? Is that one? Is that an assumption? Because think about like right, we can have a GE or a GM or estimating equation, which give you multiple rules that can satisfy this condition. I don't think
even in complete database.
Right.
Yeah, because it requires run condition. Even in complete database.
So I was just asking whether you need an assumption about the original the original complete case is identifiable. That is only one root.
No, no, because let me show you. So What we sorry about it.
Because I don't think I see any results about in the a classical complete case, we have that the root set itself is convex. I don't think I saw this result. Maybe it is this.
Okay, two things. So let me yeah. So if you look at this one here, this is the identified set, right? And this thing here, in the complete data case, if this is non-singular, then this is point identified. But here, for this identified set, we don't need to assume this is this is non-singular. It's just when this is non-singular, we are able to get the support function. And one thing remember, I probably didn't emphasize enough is that this identified set is convex. We're only able to show this for this special class of movement functions. I showed you, I showed you this general one, but I said, we don't really know much about it for general M. We don't know if it's convex or if it's connected or if it's, we don't really know. So that's why we moved on, to this special case. But for this special case, I mean, also luckily, as I said, for many parameters of interest, you can choose, your theta star in a smart way so that the movement function, in fact, does have this structure. Then for this specific class of movement functions, then we are able to claim that the identified set is convex. So I don't think this contradicts to, with what you said about the complete data case. And just to give you, for instance, an example that you raise this issue, then you see for this example, when, let me show you, see, for this example, when rho equals 1, in fact, you see there's a perfect multicollinearity here. So even with complete data, not all elements of theta star are point identified. But still, here we are, I mean, this is also, easy to sort of understand because not all theta star, can be point identified, but the sum of the first two coefficients, in fact, is point identified. So if you look at the first two coefficients individually, in fact, they are partially identified. And that's, what we have here. Our approach, in fact, applies. So we have this is straight line. But Hassani's approach does not apply because he requires immutability. So his result excludes this.
I see. Thank you.
Well, we actually ran out of time, so we have time for a very quick question if someone has any very kind question. All right, so let's thank Yanqin again. And I'll see you all.
That's brilliant. That's really great time. I think it's it's one of the best results.